Okay, so hey guys. So today we're going to start on chapter 10, and that's going to be comparing two proportions and two means even separately. Okay, so this is not like what we did last chapter where it's the mean of a difference. We find the difference first, right, and then find just the mean of those differences. Now we're comparing two specific individual groups. Okay, and we're going to be doing this with both confidence intervals and inference testing. Okay, so we're going to start with proportions today, and we're just going to work on confidence intervals as far as being able to do that. So if we want to compare the proportions, from two different groups, okay, we want to basically see if one is better than the other, right? This is how they do this for like medical testing and all kinds of stuff. You're trying to see if one group performs better or has a better success rate, whatever you want to call it. And since we're talking about, success rate, that's a proportion. Okay, so we're going to do, again today, a confidence interval on the difference between two proportions. Okay, so a couple of things that we need to go over with. Back in chapter 7, when we started doing the sampling distributions, right? We learned some basic rules about sampling distributions. Okay, and that is about their mean and their standard deviation. So what you need to understand is if that we are doing two proportions, if we're actually looking at the difference between them, the sampling distribution of the differences between them follows kind of the same rules that we learned back in chapter 7. Okay, so the three rules, and this is where we start getting all of our, random, independent, normal, and all that kind of stuff from, right? Is if we were talking about a proportion, then the sampling distribution and whatever we were doing for our open response questions would be normal as long as both your successes and your failures were greater than or equal to 10. So just type that in. Right, that's your successes right here, and your failures right here. They both had to be greater than or equal to 10 because it took care of the skewness caused by, like a really high or really low probability. Okay, remember please that the center of the distribution, the sampling distribution, the center of, the sampling distribution for the p hat was equal to p, which was the, the population proportion. Okay, so that was equal, and that was, why we were always able to do the testing, why we've always been able to do the testing we have, and that the standard deviation of the statistic, right, was this, square root formula, right, and you have that independence rule tied into that this standard deviation works, when the independence rule is in place. Okay, so we're going to kind of combine what we learned in chapter 7 with sampling distributions with what we talked about in chapter 6. I know, I can see the eye rolls. I know it's been a while. Basically, in chapter 6, we were combining random variables, right? We would add them and subtract them. And we found out that when we were adding and subtracting these random variables, that the means could just be added or subtracted, and it would be, the same thing. We did the two car dealerships, right? And when we added them together, the mean of the distribution after they've been added was literally the mean of the first one plus the mean of the second. And it worked the same way if we subtracted them, okay? So that's kind of good because that means we can just add and subtract proportions that way. The standard deviation, though, and again, I can just see the groaning or hear it, the standard deviation, when we combined random variables, you can't just add and subtract standard deviations because they're in square roots, remember? You can't just add and subtract square roots and get the same thing. So we had to square the standard deviation. We basically had to get it back to the variance, which is standard deviation squared, and then add them together and then take the square root. And remember also that even when we were finding the difference between those random variables, we still had to add the standard deviation because the standard deviation gets bigger when you're talking about two groups, even if you're subtracting their means or their proportions. Okay, so all of that basically just means that the proportions subtracted, we can do that straight out, and that's the mean of the sampling distribution. The standard deviation, though, we have to somehow combine our two standard deviations, and then take the square root of them afterwards. Okay? So take this formula right here, this P1 minus P divided by N, and imagine that you've got P1 and P2 because you've now got two proportions, and N1 and N2 because you have two samples. Okay? One sample from one population, another sample from another, and you're going to do both of these up underneath one big square root, right? And then you're going to add them together. That's really the biggest thing. It is actually on your formula sheet on that same part of the page that had this formula originally, where it said standard deviation of the statistic. It actually has it up underneath of that, if I'm not mistaken, and it literally is like difference of two proportions and difference of two means. Okay, so it's the same exact formula, we're just now having two proportions to deal with. Okay, so that being said, let's do some practice on this. And this actually is in your notes, not only the ones in Canvas that I sent out for Chapter 10 when I told you last night to start reading Chapter 10 for today, but it is on the stuff that I sent out today. So you should just be able to fill in because we really actually haven't written anything yet for our notes. So this is where we start actually filling in and doing. Okay, so we have two containers of colored goldfish crackers, right? Regular and generic, maybe. So the first one has 25% red crackers, and the other one has 35% red crackers. Okay, so we're basically looking at the difference between the first container and the second, right? Each container has more than 500 crackers, so we know that as long as we take no more than 50, we're guaranteed our independence is still good. Okay, we took a sample of 50 from the first container, the one that has 25%, and 40 from the second container, the one that has 35% red. Okay, so we are literally going to find the difference in the sample proportions of the red crackers between the first container and the second. Okay, and silly as it is, obviously this one says it has 35% more, so obviously it's got more, so it's not like we're doing a life and death situation here for an inference test. We're just, warming up on this. Okay, so the difference in the sample proportions of red crackers. Okay, so what is the shape of the sampling distribution of P1 minus, or P hat 1 minus P hat 2? Okay, so go back to our normality rule. There's our approximately normal. The only difference is that now we have two different containers, as I stated down here. We have two different containers that we actually have to work with. Okay, so we're still going to be checking success and failure to prove normality. Okay, so here's the thing. I don't know how many successes and failures because I haven't really taken or told you how many of each cracker are red. So we go back to our percentage that we're given. Okay, so 25% of 50 would be our successes, and 75% of 50 would be our failures, right? And then for the other container, 35% of 40 would be our successes, and 65% of 40 would be our failures. All right, so let's take a look. All right, there's our first container, and that's 12.5, right? And that's bigger than 10. All right, so we're good. And 75% of 50 would be 37.5. Okay, and I did make a boo-boo. I did actually forget to show that that is greater than 10. Shame on me. And that the second one is also greater than 10. So there's our first one, right? And our successes and failures are both bigger than 10. All right, go to the second one and use the percentage that you're given as far as your population. That's bigger than 10. And that one's bigger than 10. Let's add that in. Greater than 10. Greater than 10. Okay, so, and just like if we were doing a open response question, you don't just leave it at that. You also say, that it is approximately normal based on those two things. Okay, so you have to check success and failure for both containers. And again, you can also put a little note up underneath, right, that those are your successes and these are your failures. right there. Red crackers and non-red crackers. Okay? So that is the shape of the sampling distribution, and that is how we are going to prove normal in our conditions. Okay? Very, very important. What are the mean and the standard deviation of the sampling distribution? This is important because whether we're doing a confidence interval or a statistical test, an inference test, you need both of those, right, to set up your actual formulas. So let's go ahead and calculate the mean and the standard deviation. Again, based on the formulas that I was talking about. The mean is really, really easy. You know, you are literally just subtracting. That is supposed to be mu of p hat, by the way. 0.25 minus 0.35, right? So that's the mean. And that's going to equal negative 0.10. That is its mean, okay? Because we are subtracting the first one minus the second one instead of the other way around. Okay, so there's your mean. Now, the standard deviation, big formula, bear with me, okay? We're going to use the percentages we've been given, right? Now, obviously, if we were finding a confidence interval, we wouldn't have these percentages. We'd only have our samples, right? But if we're doing an inference test, we actually have this. And that's where that standard deviation changes just a tad bit. So you got your first one, 0.25 times 0.75 divided by 50. You got your second one, and notice these are all in one big square root. All gets put in together. So you're going to do a big square root in your calculator, and it's going to have two fractions in it. Not a big deal. Your calculator will do it quite nicely. And you'd still, if you wanted to do it all at once, you know, when you were doing your inference test, you could still do that. It takes a little bit. I actually went into, I forgot my calculator when we came up to Atlanta, so I actually went into Desmo's calculator online and did this. And I did this whole thing first and got the decimal for it, and then, you know, dealt with this. So, not a big deal. You can do it in parts if you want to. I know this gets to be a little bit much. Okay, so but that is the mean, and the standard deviation rounded is 0.097. So check on your calculator, make sure I didn't lose my mind, go loopy. That should be 0.097. Okay, so I'm not going to throw a confidence interval at you yet. That's, you know, the next thing we're going to practice on. But we can do a probability question, right? Probability question is really how we do an inference test. It's that same formula. So it's the probability. I'm just going to define x, you know, as the difference between them. I want it to be less than negative 0.2. That's my probability statement, right? I'm going to do this just like we've been doing since, you know, chapter 2 as far as how we write it out. So how do we set that up? It's piece minus mean, right? So the piece we're after that we're looking for is this, right? Piece minus mean divided by standard deviation. Okay, that's why they're important. All right, so let's see what we got. Piece minus mean, and I just did that because of the double negative, because I am subtracting negative 0.02 minus negative 0.010, okay, divided by 0.097, and I'm going to get my nice little z-score since we're dealing with proportion. My proportion, or my z-score, is 0.82. Remember the next step when we're doing a probability question, you know, there's our nice show up for our work. Our next step is to now write it as a z statement, since that is what we are actually doing. The probability that z is less than 0.82, you go look up that score on your z table, and you get 0.7939. So if we were to actually make a statement about that, there is a 79.39% chance that the difference, the true difference, between these two proportions is less than negative 0.02. Okay, that's what that would be in words. Okay, so we've got the, you know, the biggest things that we need to do. We need to make sure that we have our normal. We're going to state in our independence that both sets now are, you know, the same size that they need to be as far as, you know, less than 10% of the population. And we have all the pieces that we need to do in order to do an open response question of this sort, of the difference between two proportions. All right, so let's take a look as far as doing a confidence interval. right? And we just did this. We just did the combined standard deviation and the actual mean. And I'd said this already, that if you're doing a confidence interval, you have no clue what the proportion is. You know, like in the goldfish crackers, we know what it's supposed to be. In a open response question, all you're going to be given is the counts, right? And so you don't have p, you just have p hat, and that's what you use. Okay, so here's our formula for our confidence interval, right? Statistic plus or minus your critical value times the standard deviation of your statistic, which is what we have. Okay, and we just talked about that as far as extra piece. 2 sets of them. Everything has to be greater than 10 if it's a proportion. Both groups would have to be greater than 30 if it's a mean. And yes, I can just see the little eye rolls again. Yes, if you have 2 groups and you're doing a mean and both groups are less than 30, you're going to have to do 2 histograms. But again, it's not a big deal. You know, it just takes a little bit of time, a little bit of effort. You're going to probably be putting the data in the calculator anyway. Okay, so let's actually go through a confidence interval for the difference of 2 proportions. Okay, so state plan do conclude. This is what you're going to be, you know, typing in or writing in on your notes. So, country music, and yes, this is actually an example from the book. Is country music more popular with young whites than among young blacks? A sample survey compared 567 randomly chosen blacks aged 15 to 25 with 634 randomly chosen whites in the same age group. The study found that 130 of the blacks and 352 of the whites listened to country music at least 4 times per week. Okay, so we're going to do a 95% confidence interval for the difference between the proportions. Okay, so state plan do conclude. All right, so state. Well, since this is a confidence interval, we're not doing ho-ha, we're doing what we're actually doing. We're stating what we're doing. We're going to estimate the true difference in proportion. Remember to get in the word true. Some of you lost points on the last test on your open response because you keep forgetting that word true when you're defining your variables. Estimate the true difference in proportion of people who listen to country music, and make sure, please, that you are stating which way you are subtracting. This is just like doing the mean of a difference, which is what we were doing before. You have to state the way you're subtracting. Otherwise, you're going to go from an E to a P on your state part, because they don't know if your do and your conclude follows your statement, okay? And especially when we're doing the ho-has, you have to, I mean, the way you subtract really determines what your alternative hypothesis is going to be, so it has to match. Okay, so estimate the true difference in proportion of people who listen to country music, white minus black, and you can also say people age 15 to 25 if you want. Okay, so plan. Random, yes, randomly chosen. It does say randomly chosen, given in the problem. Okay. Independent. We have now 2 groups, so we have to list them each in the independence rule. There are more than 567 times 10 blacks. There are more than 634 times 10 whites, age 15 to 25. It doesn't say where, so you could even put age 15 to 25 in the world, okay, because that actually would be part of it. Okay, so the random, this is the one we were talking about, not random, normal. This is one we were doing before where you have 4 different things to check now. So you have normal. You have white, 352 is greater than 10 successes, and 282 is greater than 10 failures. If you don't know where I got this, up here, again, it says 352 out of the 634 listen to country music. That's considered a success. Subtract 634 minus 352, and you're going to get 282 failures. Same thing with the black, 130 successes, and 130 taken from 567 would be your failures, so that would be 437. Now, I know a lot of you like to write it out, and that's fine. You're going to get the same number, though. It's 352 out of 634 times 634. right? Because your sample size for the whites is 634. Your sample size for the blacks was 567. And if you write this as a fraction, 352 out of 634, it's the same exact thing. You're not going to get dinged for writing it as a fraction as long as you put the p times the n. You won't even get dinged if you actually find out whatever the fraction is for 352 out of 634. Let me grab my phone calculator real quick. 352 divided by 634. You won't even get dinged for stating this as 0.56 times 634 is greater than 10 successes. And that's fine because that's technically NP. Okay, to me this is just an easier, shorter way knowing that I'm just basically counting up successes and failures from both groups. Okay, the do. This is a confidence interval, so remember it is statistic plus or minus critical value times the standard deviation of the statistic. And it's going to be pretty big, and you're going to get all those decimals, okay? So, and I could have just as easily put 0.56 and 0.23 here as well, and that would have been fine. 2 places is normally pretty good for this. If you wanted to go further, I believe it was 0.5552, and then the other one would be 130 divided by 567. The other one would be 0.2293 if you're going to round it correctly. And that's fine as well. I'm just putting those up here so I can actually see my counts. But yeah, you can put 0.56 and 0.23 up there if you want. I'm using 1.96. The other question on that one is yes, you can still use 2. If you're doing a 95% confidence interval for proportion, you're always allowed to use 2 because of the empirical rule. So, but if you pull it off the t-table, that bottom row on the t-table, you're going to get the 1.96. So this is the setup, that big long honking thing. Okay. And so then I didn't actually write my interval up here. I should have. I included it in my conclusion, but I forgot to put it up here. So forgive me for that. Okay, so the conclusion. And again, there are several different ways to write this. You know the keywords by now. You need to say that you're 95% confident. You need to say that it's the true difference in proportion. You need to say captured or contained by the interval, right? You have to put those in the conclusion. So there's lots of different ways that you can phrase this, but those things have to be included in the conclusion. So mine, we're 95% confident that the true difference in proportion between white and black people aged 15 to 25 who listen to country music is captured by the interval from 0.2739 to 0.3779. Okay? So that would be it. We're going to actually use the same data, and we're going to run an inference test either tomorrow, probably Wednesday though. And it's that same thing that I was talking about last chapter. If you're doing a 95% confident, that would correspond to a double-sided, basically a not equal to inference test at a 5% alpha. And notice what is not in my interval is 0. Right, so definitely there's a difference between the two. So, but for today, we're just going to do confidence intervals. I'm going to give you a couple to look at tonight in your chapter for your homework, and then we're going to do several more of these. It's actually already in the notes that I emailed to you. I think there's like 2 or 3 more examples, and we'll work through a couple more tomorrow just to make sure everybody's comfortable with it. So, real quick, tech time, in your calculator. This is not, well, yeah, stat test, but this is a 2 prop. We're now looking at 2 proportion Z interval. If you don't want to show it out, please remember that you are doing a confidence interval with 2 proportions, or confidence interval on 2 proportions. You can do it that way too. Using a Z distribution. And I dinged a couple people on their open response on the last test because they literally just wrote like one, I don't even know if it was a one prop z-test or whatever it was. And I'm like, we don't do calculator speak. That's how it's abbreviated in the calculator because otherwise it wouldn't fit. You need to state out what you're doing. Okay, so we're doing a confidence interval with two proportions using a z-distribution. You could also say a confidence interval for the difference in two proportions, but with is enough because they know at least that if you're using two proportions, you're finding the difference between them. Okay, so what I want you to look at tonight, 1, 3, 5, 6, 11, 14. If you have any questions on it, please send me a remind message and ask. And I do have my book with me, so you can just ask me a question based on a number. Take it easy, and I will talk to you tomorrow.